Hi guys, Miss O'Connell here. So today we're going to be starting a new unit. We're going to be talking about simple harmonic motion. Okay, which we'll talk about what that is in a minute or two. Today is the 23rd, so please make sure that we're writing this down in our notebooks. Okay, so 3/23/20, simple harmonic motion. So we're going to start off today with a do now. So I want you guys to consider where you see, hear, or feel vibrations in your everyday life. Okay, so take a minute and pause the video. Think about where have you felt, seen, or heard a vibration as of lately, and jot it down. Okay, so some common answers that we may have come up with here, probably vibrations due to a sound system, a stereo. If you've ever pulled up to a red light, right, and the car next to you, their music is so loud that their car is physically vibrating and you can hear that vibration. Okay, so it occurs due to speakers or sound waves. We may also see vibrations when we throw a pebble into a pond or still body of water. We notice the rippling of water waves as they move across the surface of that pond. Okay, guitar strings, any stringed instrument, we know that string vibrates. Our cell phones, okay, our cell phones are probably on vibrate right now as we speak. So we have seen and heard vibrations in our everyday life, but do you know what a vibration is? Can we define what a vibration is? So what's most interesting about a lot of things that we talk about in physics is that we have seen it before. We've used it before. And we have some understanding of it, but it's difficult for us to describe or measure mathematically because we have not looked at it from a scientific perspective yet. So that's what we're going to do today. We're going to take a look at what a vibration is. What does it mean for objects to vibrate? Why do objects vibrate? And how can we measure vibrations? Okay, so if you have a ruler at home, I'm going to ask you to pause the video and go find yourself a ruler. If you don't have a ruler, don't worry about it. Okay, but if you are to use the ruler as we move through this discussion, it's going to help you out a little bit. It's going to allow you to imagine or see the definitions that we're talking about. So if you're at school, I'd hand you all a ruler right now. Okay, so if you have a ruler, please go grab one. Okay, so we're going to define what a vibration is. So yes, I know that my diagram here has two right hands. Okay, that was obviously an accident. If you have a ruler, what I'm going to ask you to do is on your table, you're going to suspend the ruler off the table. Use your left hand to secure the ruler onto the table, holding it in place. You're going to, with your right hand, apply a force to the free end of the ruler. Okay, you will see that that ruler moves up and down, and it makes a quite annoying sound that your family members are probably not thrilled about hearing right now. Okay, I challenge you to possibly be able to play a song with those vibrations. Okay, so to get it out of your system, take a minute, pause the video, and give the ruler a couple vibrations. Okay, so you have now unpaused the video, meaning that you are ready to talk about what a vibration is. So I want you to think about the motion of the end, the free end of the ruler that you applied a force to. How can we describe the motion of the free end of the ruler? Okay, so usually we say up and down, back and forth, right? So we have up and down, back and forth movement. Think about where the ruler begins and ends its motion. Okay, so the free end of the ruler would begin and end its motion in the same location. At that location, there is no external forces applied. So the ruler moves up and down, and it starts and stops at the same position. At that position, there is no forces applied. Okay, so that ruler is vibrating. So we can define a vibration, or as physicists say, an oscillation, which is the same thing. A vibration and an oscillation are synonyms for each other, the same thing. An oscillation is up and down movement, or back and forth movement, about an equilibrium position. And if we remember from our force unit, what is an equilibrium position? It's a position in which all the forces are balanced. So before the ruler starts vibrating, and when the ruler comes to rest, there is no external force acting on the ruler. Its acceleration is 0 before you apply force and when the ruler comes to rest. So it'll move up and down about that equilibrium position. And that's the definition of a vibration. Okay, so let's talk about why things vibrate. So technically, vibrations are, although they're common in nature, it's kind of unusual how natural they are. Okay, because they require you to apply some type of force, a very specific force. Okay, that has characteristics unlike other forces that we've studied so far. So what I want you to do, again, you're going to take that ruler, suspend it from your table, okay, as seen in the picture below. Take your left hand, put it over one end, your right hand on the free end, and you're going to apply a force without releasing. Apply a force, so push down with your right hand on the free end of the ruler. Think about what you feel on your left hand. Okay, so as you're holding that ruler down, you can feel the opposite end, the left end of your ruler, applying a force to your hand. Right? That force is in the opposite direction as the force that you are applying, the end of the ruler. So the displacement of the ruler and the direction of the force that you feel on your hand are in opposite directions. Okay? If you actually remove your left hand from the end of the ruler and apply a force to the free end of the ruler using your right hand, you will see that that ruler does not actually vibrate because there is no securing or restoring force to keep the end of the ruler in place. So in order for the ruler to vibrate, or for objects to vibrate, there must be a force. We call that a restoring force. We call it a restoring force because that force restores the object back to its equilibrium position. Okay, so to oscillate, there must be a restoring force. That restoring force, just like the force of the ruler on your hand, is directly proportional to the displacement. When you push the end of the ruler down, the force you feel on your hand is up. The further you push the ruler, the larger the force that you feel on your securing hand, your left hand. So the greater the displacement, the greater the force. They're directly proportional, but in opposite directions. Okay, at each instant that the ruler vibrates, okay, its position, its displacement changes. Because its displacement changes at every second, that force is going to change in every second. So the force technically varies with time. Okay, so for objects to vibrate, there must be a restoring force. That restoring force is directly proportional to the displacement of the object. As displacement increases, the force increases, but they act in opposite directions. As an object vibrates, its displacement changes at every second, meaning that the force varies with time. We will talk more about characterizing this restoring force later in the week. Okay, but objects vibrate due to a consistent restoring force. Okay, and that's all objects. Okay, birds' wings, your heartbeat is a vibration. Okay, restoring force allows that object to continually vibrate. But the case of your heart, however, right, that force is constant and consistently is applied. Okay, so a vibration is up and down movement about an equilibrium point. Objects vibrate due to restoring forces. How can we describe repeated vibrations? Okay, so objects like a mass on a spring or an object on a pendulum will consistently vibrate back and forth. This repeated or periodic vibration, we call that type of motion simple harmonic motion. So simple harmonic motion, also known as periodic motion, occurs when objects or systems repeatedly vibrate or oscillate. Okay, and these repetitive vibrations occur in equal time intervals. So the amount of time it takes per vibration, per back and forth movement about an equilibrium position is constant. Okay, and actually this was hypothesized by Galileo. So he was studying medicine and he was attending church on a Sunday and he was bored. So he's kind of zoning off during some type of lecture or sermon. And he noticed that the crystals in the chandelier, as they swung back and forth, the amount of time that it took each crystal to swing from some max position to some max position was equal. Okay, so that equal time interval, we call that a period or periodic motion. Okay, so repeated vibrations or oscillations, we call that simple harmonic motion. Okay, so our next goal or question is, how do we measure simple harmonic motion mathematically? So we know what a vibration is, we know why it occurs. How do we measure these repeated oscillations or vibrations? Okay, so we measure simple harmonic motion in 3 ways. So the distance that you stretch the end of your ruler. Okay, so you apply a force to the end of your ruler. The distance or the displacement that you stretch that ruler, we call that the amplitude. So amplitude, which we use a capital A as the variable to represent, the amplitude is the maximum displacement from the equilibrium position, measured in meters. So the amplitude of our ruler would have been the distance below the desk or table that you stretched the end of the ruler in meters. That is the amplitude. That's its max displacement or max position that the object can occupy during its vibration. And we measure that in meters. Okay, so it's a very specific type of displacement. Max displacement from equilibrium, we call that the amplitude. The next way in which we measure simple harmonic motion is called frequency. Okay, you've probably heard that word before. If not, we've probably heard the word frequently. So if I were to ask you, how frequently do you ride a bike? I'm really asking you how often or how many times do you ride a bike? So to measure that, you would have number of bike rides, okay, and the amount of time, whether it's a week, month, etc. Would answer the question, how often? When we're talking about the frequency or how frequently a vibration occurs, we're asking or determining the number of vibrations or oscillations that occur per unit time. In this case, per second. So frequency, which we use a lowercase f as the variable to represent, the frequency is the number of oscillations per second. And we measure frequency in hertz. Okay, so not like the rental car company. Okay, hertz as in the radio stations that you turn into. Okay, so 92.3, right, measured in megahertz. So it's 92.3 megahertz. That's the frequency in which you're tuning into on your radio. We use the abbreviation capital H, lowercase z, for hertz. Okay, and a hertz is equal to 1 over second. It's the inverse of a second. So it's the number of oscillations per second. The final way in which we measure simple harmonic motion is period. So just like the periods in our school day, right? Each period is 45 minutes. Okay, the period is a consistent amount of time. Okay, it's the amount of time required for one complete oscillation or vibration. And we measure it in seconds. So period, we use capital T as a variable to represent. Must be capital. Okay, lowercase t represents time. Capital T represents period. Period is a very specific measure. It's the amount of time required for one complete oscillation or vibration. Okay, you cannot use a lowercase t to represent that. It must be capital T. So you might be thinking that period and frequency sound very similar, right? How are they different and how are they related? So we're going to go into that next. So period versus frequency. So period, we say, is the time per oscillation, the time it takes for one oscillation or one vibration. The frequency is the number of oscillations that occur per unit time. Okay, so looking at period and frequency, can we denote how they are related? Okay, so period is time per oscillation and frequency is oscillation per time. So they are proportional. Okay, technically inversely proportional. So I would take a second and write the period and frequency equations on your note card under SHM. Okay, so SHM stands for simple harmonic motion. That's the abbreviation that we usually use. So pause the video and add those two equations to your note card. Okay, so the formal equation, right, for period and frequency is that the frequency is equal to 1 over the period. Okay, we measure frequency in hertz. The period is equal to 1 over the frequency. We measure period in seconds. Okay, so they are inversely proportional to one another. Let's take a look at a situation in which we'd be given frequency or period of a vibration, and we need to find the opposite. Okay, so let's apply these equations to an example. Okay, so example 1, a guitar string vibrates with a frequency of 20 hertz. Determine the period in minutes. Okay, so we know that if the guitar string vibrates, it's going to move up and down about an equilibrium position. We're told that the frequency of that vibration is 20 hertz. So 20 vibrations per unit time. We want to find the period. Okay, we know that the period and frequency are inversely proportional. So the period will be equal to 1 over the frequency. We know the frequency is 20 hertz. So we're going to plug in 20 hertz for lowercase f frequency. Okay, this over here should be a lowercase f. It auto-corrected to a capital F there. So this should be a lowercase f for frequency, just like in the equation here. So 1 over 20, I have 0.05 seconds. Okay, our hertz is 1 over second. Okay, so if I divide 1 over seconds, okay, that becomes seconds. So I have 0.05 seconds. Our last step is we need to convert from seconds to minutes. To convert from seconds to minutes, we need to multiply by the ratio 1 minute divided by 60 seconds. So that our seconds cancel out. We're left with just minutes. So we'd find that the period in minutes is 0.0008 minutes. So not the most practical unit. Okay, but you will have to convert from seconds to minutes, minutes to seconds. Okay, possibly oscillations per second to hertz. Okay, so good practice in unit conversion there. All right, so you guys can try the questions in the Google form. Okay, if you have any issues, you know where to contact me. Have a great rest of your day, and I will talk to you guys tomorrow.